Okay, so good evening. Let's get started with the summary of the last class. Um, I talked about the four major differences between PVD and CVD processes, physical vapor deposition and chemical vapor deposition process. So PVD relies on solid or molten source, whereas the CVD process, all the CVD process use gas precursors. That's the main difference. And PVD requires high vacuum. Vacuum is not required in the case of CVD. Another point of importance is there's a general absence of reactions in the case of PVD, whereas CVD growth process is all about reactions leading to the formation of the thin film. I also said that there are advantages and disadvantages on both sides, and there are a number of techniques that we can list on both the sides. Then I also mentioned that this important relation between the pressure versus temperature plots, log of vapor pressure as a function of 1 by T. These linear plots are called the Arrhenius plots. And, in these plots, you get information about the melting points of the system. And these give basically guidelines as to what kind of alloying is possible and what is the information with regard to the vapor pressure when you're, thinking of making an alloy composition or an intermetallic. And I said the ideal situation in terms of thermal evaporation, which falls under the category of physical vapor deposition. Ideal situation is evaporation without dissociation, which doesn't happen most of the time. So you have evaporation with dissociation, decomposition. I said that the solution is having different evaporation sources. In fact, this process has led to the invention of a very sophisticated thermal evaporation process called molecular beam epitaxy. I also mentioned an important point where, as a thumb rule, a melt is always required if the element in question does not achieve a vapor pressure of greater than 10 raised to minus 3 torr at its melting point. There are some very good examples. Chromium is a very good example where you can start depositing chromium. That means atoms from a chromium source can be removed 500 degrees below its melting point, because 500 degrees below its melting points, the vapor pressures reached those values greater than 10 raised to minus 3 required for evaporation process to be possible. Okay. So let's start with evaporation of alloys, and a binary alloy consisting of two elements, A and B. Alloy consisting of three elements, A, B, C, D, and then you have intermetallic compounds where you have a specific composition. I also mentioned yesterday that as long as the vapor pressures of these different elements is matching, then there is no issue. But you may need an alloy where two elements have two different vapor pressures. So metallic melts are solutions that are governed by well-known thermodynamic laws. When the interaction energy between metals of element A and B, metal combination consisting of two elements A and B, forming a binary alloy. When this interaction between A and B of a binary alloy melt is the same as that between interaction between AA and BB atom pairs, then no preference is shown for atomic patterns to form. this is the ideal straightforward issue. Yeah, that's what. So the above argument always holds good for ideal solutions. But then we have Raoult's law that states that vapor pressure of component B, if you're considering two elements A and B, what this law says is the vapor pressure of the component B in solution, because you're melting it, so you have everything in solution, is reduced relative to the vapor pressure of the pure form of B. So the vapor pressure of pure form of B is PB naught, and the vapor pressure of B in solution form, in the molten solution form, is PB. The vapor pressure of pure B is in proportion to it, is proportional to the mole fraction. Okay. And so this proportionality is given by this simple relation. The vapor pressure of the solution, PB, is equal to XB, that is the mole fraction, times the the vapor pressure of B in solution. Okay, so the vapor pressure of the solution of B modifies in this way. So it is the vapor pressure of the pure element B times its mole fraction. Okay, this is important to consider. I'll tell you why. So metallic solutions, as I mentioned, are not ideal. So this means either more or less of B will evaporate relative to the ideal solution case. In the ideal solution case, you expect both A and B to evaporate in equal volumes. But then in most of the cases, since the mole fraction has to be considered, you are always away from the ideal case, which means that either more or less of B will evaporate relative to the ideal solution case. So depending on whether the deviation is positive or negative. A positive deviation occurs because B atoms are physically less bound to the solution, facilitating their tendency to escape or evaporate. So I have, I told you in the previous class that in the case of alloys and intermetallics, unlike in the case of inorganic compounds, where the bonding between metal atoms is much lower than that you normally have between in covalently or ionically bonded compounds. Metal atoms can be separated out from the alloy easily, which means that in thermal evaporation process of alloys consisting of 2 or 3 or 4 elements, in most of the cases, you'll see the elements coming out of the matrix, the charge, as separate entities, not as AB or ABC alloy composition. Of course, this is true in thin film growth process. As we go to the other process, you'll understand that this is true in most of the cases, because the whole idea of thin film growth of even inorganic compounds that are grown by other methods is to break up that inorganic compound into its individual constituents and then make these constituents to recombine into a regular periodic lattice. Okay, so in real solution, you have PB is equal to AB times PB naught, where this AB is the effective thermodynamic concentration of B, which is also known as the activity, right? Okay. So the activity is in turn, this activity, AB, is in turn related to XB, the mole fraction, through an activity coefficient, gamma B. This should be gamma here. There should be a gamma there, no, it's missing. So it should be activity coefficient is gamma B. So you have the effective thermodynamic concentration of B, which is the activity, and this activity is in turn related to XB through an activity coefficient, which also means that each element has a different activity coefficient because of the differences in mole fractions, the differences in melting points, hence the differences in the vapor pressures. So this AB is equal to gamma B, which is a activity coefficient, times XB. So the ratio of the fluxes of A and B atoms in the vapor stream above the melt is then simply given by this relation. Okay, again you're looking at the vapor stream. That means the flux of A atoms and the flux of B atoms. The ratio of the two fluxes, phi A by phi B, is equal to gamma A XA PA naught by gamma B XB PB naught times root of MB by MA, the molecular weights. So for ideal situations, we consider XA plus XB is equal to 1. So a practical application of this equation is difficult because the melt composition changes as evaporation produces or evaporation proceeds. Look, I have A, I have B. We don't have an ideal solution, right? Which means A and B are not evaporating at the same rate. Okay. So when they're not evaporating at the same rate, that means either A or B starts evaporating first. Which means what? Your composition, your melt composition is doing more of A initially, let's say, and so more of A atoms go on deposit on the substrate, and then B atoms go on deposit on the substrate, and then you must ensure that there is sufficient substrate heating in order for the A and B atoms to react with each other to give that alloy composition. Okay. So the activity coefficients also change with time. When this is happening, right? When the melt composition changes as evaporation proceeds, you also expect the activity coefficients to change with time, because it's the whole process is time dependent. If you have an alloy charge of say 10 grams, and then for the given initial thermal energy, you know how much time it takes for the entire alloy melt to vaporize and form into a thin film, right? It can't happen in a split second. So there's a time scale involved. Within that time scale, you will see the activity coefficients changing. Okay. Now let's consider the problem of estimating the approximate aluminum copper melt composition required to evaporate films containing 2 weight% of copper from a single crucible. It's a simple example. So I have a aluminum copper alloy, right? Now I have the melt composition. I need to evaporate and get a thin film of this aluminum copper melt composition. And so the problem here is the estimation of the approximate aluminum copper melt composition required to evaporate films containing 2 weight% of copper. That means 98 weight% of aluminum from a single crucible. I'm not using 2 different sources. I'm using a single source, right? Heated to 1350 Kelvin. So of course, I said initially, I can use 2 different sources, heat this one, heat that one. Aluminum and copper have different melting points. That will easily solve the problem. But aluminum has lower melting point than copper. And then I also want to maintain that weight% of copper and aluminum. So the evaporated film should have a copper weight% concentration of 2 weight%. And then the alloy I'm evaporating using just a single crucible. So what is required here? So you have basically your phi AL by phi CU is equal to 98 times M of Cu and 2 times M of Al. This is a simple ratio of 5A aluminum to that of copper. Now, from the vapor pressure data, so then you can go back to the vapor pressure data because you need some information to be plugged into that equation, right? What you need is the vapor pressure information. This you can straight away get it from the vapor pressure tables, okay? Now from the vapor pressure data, this ratio is 10 raised to minus 3 there divided by 2 into 10 raised to minus 4. So you have those parameters in place, and you have the other parameters. Now we can easily find out. Let's assume for simplicity that the activity coefficients are same for copper and aluminum. So your gamma Cu is equal to gamma Al. Then what is this ratio is a question to calculate. So what we are trying to do is to get 2 weight% of copper and 98 weight% of aluminum. Is it okay to start with the same weight% ratio or not? This is always very important in thermal evaporation. In fact, many people make a mistake of taking the same weight% composition that you need to finally get on the thin film. No. So what you start with is a nominal composition in this as a source. What you get there is a final composition. So there is no guarantee that the nominal composition that you take in the crucible is reproduced directly with the same percentage, weight percentage on the substrate. Because all these simple things that we have seen in the last 2 slides is involved. Okay, now you see that. Now this ratio turns out to be, if you plug in all those values, 15. What does it mean? This means that the 2 weight% of copper aluminum vapor stream requires a melt, right? The melt with a 15 to 1 mole ratio of aluminum to copper. Therefore, the original composition should be enriched to 13.6 weight% of copper in order to compensate for the preferential vaporization of aluminum. Because you see, when in a copper aluminum in a copper aluminum alloy, when you start giving thermal energy, it's the aluminum ions or atoms that start coming out of the matrix before the copper atoms come. So in order to compensate for the loss of copper on the other side, you need to enrich the initial composition by this much weight% of copper. So the original composition should be enriched to. So what is the problem that you started with? The problem is to estimate the approximate aluminum copper melt composition required to evaporate films containing 2 weight% of copper from a single crucible. And it turns out that you need the original composition should be enriched to 13.6 weight% of copper in order to compensate for the preferential vaporization of aluminum. So these simple calculations have to be done for every alloy composition that you start with. So this is called taking excess of one of the elements by taking into consideration the vapor pressure components and the activity parameters of the elements involved during the process of evaporation. So that's why a practical way to cope up with severe fractionation is to evaporate from individual sources. In this case, dual sources, because it's a binary alloy AB, right? Maintained at 2 different temperatures. Well, this process, in fact, as I told you, has led to the invention of a much better a very sophisticated technique called molecular beam epitaxy. Yeah, so you have two different sources, and I have copper in one, aluminum in one, and you vaporize it, but then just vaporization of copper and aluminum is fine, but you need to also control the vapor fluxes. That's the key. Now, and that point is well taken care in a technique called molecular beam epitaxy. Okay, so the refractory metal sheet sources are used. You see what you have seen in the previous one is these all these various forms of crucibles that can be used for evaporating elements, and what you have here is normally those crucibles, I mean, they can be obtained in different forms. If I have a sheet of tantalum or molybdenum, I can make it in the form of a bowl or a boat, or some kind of a container that can hold the charge before the melting happens. So tungsten, tantalum and molybdenum are the normal refractory sheet sources, because these elements have very high melting point. So you can easily heat the charges to high temperatures for melting to happen, and there'll be also less reaction between the these sources, tungsten, tantalum, and molybdenum, because they have very high melting points. So in order to avoid the reaction between these elements and the compounds or elements whose thin films are to be deposited, these refractory metal means high melting point metals. Okay? But then there are cases where the charges that require high melting points to create the melt, where you have to heat the element to very high temperatures. There could be a reaction happening between the crucible and the molten part of the alloy. This is one of the another issues of concern in thermal evaporation. So these sources are made into different shapes, boats. As I told you, I'll show you the picture of how many different sizes and shapes you can make these, refractory metals into. There's sublimation furnaces. The efficient evaporation of sulfides, selenides, and some oxide is carried out also in sublimation furnaces. The evaporant material, which is in a pellet form, is surrounded by a radiation heating source, and tantalum sheets are used to make these heaters. Okay, right. So that's what. Now you have the chamber. You have a heater there. You have a crucible, and you give a power. You give enough power for the heater to reach temperatures required to melt the source. And then you, from the melt, when the melt starts evaporating, because you also have created a vacuum there, and vaporization happens, leading to the vapor atoms settling down on the surface, leads to a thin film formation. And always remember, it depends on the kinetic energy of these evolved species from the source onto the surface of the thin film substrate that determine the crystalline quality of the films. I already mentioned that thermal evaporation process is a low energy process, because the heating that you provide to the source only helps in melting the elements that are present in the melt, or whether they are individual elements or in the form of a binary alloy. And so there's no additional energy that these evaporated species get. It's just the thermal energy. That's the reason why, first of all, the process is not directional. These species can go all over the place, and the kinetic energy is very low. So you don't expect a high degree of crystallinity of thin films on this side. So thermal evaporation, for all practical purposes, is used as a It's a very good simple technique for metallization. So if I have a surface on which I want to give metal contacts to do some experiments or to make devices, thermal evaporation is a good process. Yes, this is all for your reading. You know, what all I mentioned, crucibles can also be made of oxides, boron nitride, graphite, refractory metals, because these are all high melting point compounds. These crucibles are heated by tungsten wire elements wound to fit snugly around them. Other crucible sources rely on high frequency, these are radio frequency induction heating is possible, right? And the laboratory scale film deposition of, say, aluminum oxide or refractory oxides encased in a tungsten resistant heater, conical baskets also are used. Yeah, you'll understand better if you look at this. It all depends on the requirement. I want a small amount of charge to be heated, so I make a small boat like that. So this is from a tungsten sheet. I can easily cut it and fold it in such a way that, you know, I make it into any specific form I want. You know, bigger boats. Because I'm melting 15 grams of the alloy, and you see the bigger ones. And you also have these wire heaters, no? Very famous wire heaters. That's because, see, why I want a wire heater or a heater wound in the form of a conical basket. You see that? This is a conical basket, or in this form, is for the following reason. So I have a charge inside a boat made of aluminum, molybdenum, the refractory element. So you take it to its melting point, and this melt spreads all over. It just spreads, gets liquid, and so that means the area of the evaporating element has increased. Okay, and there is also a possibility of a reaction happening between the the crucible material or the boat material and the molten element or alloy. So to avoid that, I want to melt that small piece of charge, right? And then I don't want the melt to spread, which happens in the case of when use these boats. So I can use a coiled heater like this, right? But there's a problem here. Now, so you can imagine this. Now I have a coil like this, right? I put a charge on top of it, a small lump of metal. So when the metal starts melting, it loses its volume, right? So after a certain stage, so the melt can drop down of the heater. That's it. So that means until the point that the radius of the the ingot or the metal piece is larger than the radius there, it's held there. Of course, when the melt is coming down, it doesn't just drop off immediately. It will hold on to the walls of the this coiled heater because of surface tension. Because after all, you melted it, right? So it's still in the form of a lump, and then the surface tension holds on to it. So it is still possible for us to see that by the time the last piece of the molten drop comes down, everything is evaporated. But what is happening in that process? So now you can imagine this is a 1 inch winding. Now you start there, and this is a substrate. So we always want to keep the distance between the source and the substrate constant, right? You don't want to vary that, because this depends on your also, this determines your deposition rate. Now what is happening when, of course, your substrate is fixed. Now the initial charge in the case of a wire wound in the form of a heater, which is 1 inch in length, the charge starts there and then it drops. That means you have changed the distance between the source and the substrate by 1 inch, which is not good. And in order to avoid that, to some extent, these conical baskets are used, shortened length. And the whole idea is, you know that as the melting process is on, the charge which is in a solid form starts losing its volume. And as it becomes smaller and smaller, right, it is pushed through this, the conical basket arrangement, where it is still held at each of those rings. Unlike in this case where it can go down much faster, right? This is a very logical way of designing, these wires in a conical form. So it all depends on one's requirement, especially if I want to make gold contacts, right, which are required for some experiments. I can only afford to use a small piece of gold to be melted. So I don't want to use a large boat like this, in which once gold melts, it spreads all over. So you end up evaporating some form of gold, but then most of the gold remains as a coating on top of the molybdenum sheet itself, if you're not completely evaporating dark gold also. Yeah, you see that? These are more sophisticated way of making these boards. You see that, how small it is? Yeah, I can use a small piece of 1 gram of gold, and then I can create vaporization leading to the coating of our choice, right? And these are all small depressions that created in these molybdenum and tantalum boards. Some of these are expensive, but they can also be reused. For larger quantities, you can go for this type of crucibles. Yes. So all said and done, in most of the cases, when let's say you fill this with aluminum, okay, and then you get a coating of aluminum, and let's say this aluminum sheet coating, thin sheet of aluminum also superconducts at very low temperatures. And today there are lots of devices that are made of aluminum. For example, even superconducting qubits. It's a lot of wonderful involved research. Niobium, for example, I can use it as a superconducting qubit, but these are all low temperature devices, but very useful devices. So I want to make sure that when I'm depositing, so if there is any impurity, when I get a layer of aluminum or niobium or some other low temperature superconducting materials, right? If there are some impurities coming from these crucibles, because after all you're heating them to their melting points, then the physical properties can change. So we don't want that to happen. So is there a solution whereby, so even in this case, when you're using these wires, wound in the form of these coils of conical baskets, still there could be a reaction between the wire material and the molten element. It's unavoidable, right? There could be some atoms that could diffuse into the melt. Okay, so what is the solution? If I want to melt something, I still want to melt it, but I don't want the crucible to, or these boats or these baskets to induce any kind of impurity into the charge. So the solution is, imagine if I have a source inside, right? Of course, this source is surrounded by heating elements. The whole thing is heated. So when the material inside melts, it also spreads all over. In fact, you see always a thin coating of the material that was melted in the previous run. So if you want to use the same board, you can use it, or crucible, you can use it for the same element or alloy in the next run, or you need to have a fresh board because it already has a coating at the bottom. Because you melt it, you also don't take the exact composition that that evaporates completely 100%. So some part of the alloy or element is always left behind. So that forms a coating. You can imagine, right? You melted it, and you got sufficient thin film on the substrate. Then once you stop the process, the remaining melt is solidified and it forms a thick layer. That's it. The only way you can use the crucible is you can, if you're depositing the same alloy composition, then in that case there's no contamination problem. You can't use it for any other alloy combination because then you're putting the other elements that are already there. All right? Or you have to use a fresh one. So this is also an expensive process. So, but the process of the melt spreading out itself can cause contamination. So how do I avoid that? Can I have a method whereby I heat the charge? So let's say this crucible is completely filled with charge, or even this one is completely filled with charge. Can I heat it locally, just with a local heating source? See, that's how the beautiful evolution in thin film growth processes happen. It is possible. So how is it possible? Imagine if I have a high energy source and I make the high energy to impinge on, a crucible in which you fill it with a given material system that needs to be deposited. And I'm not heating the entire crucible and melting the whole thing. And with a radiation source, I should be able to melt only a part of it. And which means I'm not making the melt to flow around in the inside of the crucible. Beautiful, is it not? So that's how the electron beam evaporation evolved, right? And today, electron beam evaporation is the most popular way of evaporating metals and alloys. There is no contamination involved, and it's also a high energy process because it's all because you're dumping a lot of energy onto the charge, and so the evaporation also can happen instantaneously. That gives a lot of energy to the emanated atoms from the molten source. So the contamination is the main problem in resistively heated evaporation sources, including contamination by crucibles and heaters. Okay, so input power levels are limited in thermal evaporation. I mentioned this already. It's difficult to deposit high quality thin films of high melting point of elements and alloys. Even higher low melting point elements, the evaporated species have always low kinetic energy. So you don't get highly crystalline epitaxial thin films. So the solution is electron beam evaporation. It's a beautiful way, and the way electron beam evaporation has evolved, it has also brought in many other new techniques. Okay, you'll see some of them. So electron beam heating eliminates the above disadvantages. No, there is no crucible contamination, and this also gives also gives preferred evaporation. You see, if you go by the theory of the thin film growth process, in order to get directional evaporation, so I'm evaporating from here. I want the emanated species to move towards the substrate in a highly directional way. But in thermal evaporation, it's not happening. It's non directional because there is not enough energy for these species to move in the upwardly directed way. So this requires a lot of energy, and so they're all spread in all directions. They coat the substrate, but the entire interior of the your chamber also. So the theory says that if you have a point source, you'll have a highly directed, evaporated species. The evaporation will be highly directional. So this is one advantage. Using electron beams, I can, of course, I'm actually converging a lot of energy into a small region. So the energy density is very large there. I'm making the energy density so large that I can cause instantaneous evaporation of the charge. So without touching the entire volume of the charge. This is a great advantage. So the purity of the evaporant is ensured as only a small amount of the charge is melted, right? So the whole crucible, I fill it with the entire charge, but then my electron beam is point sourced, right? And then I don't have the problem of melting the entire charge. So the unmelted skull material next to the cool hearth, that unmelted one is the skull is the molten solidified part of the metal or alloy that I mentioned in the case of thermal evaporation. That's called a skull. It forms a coating. So the configuration of the electron guns are very essential. How to produce it? It's easy. You can produce electrons like we produce electrons to in the case of electron microscopes. I said there's a need for you to produce electrons. Electrons are produced thermionically by emitting heating filaments. It's easy. You have a filament, you pass high enough current, and then electrons are produced. And those electrons in the microscopic case are made to accelerate in that 1.5 meter long columns, and they go and impinge on the target material, and you get all kinds of analysis, the surface morphology, the elemental composition, etc., etc. But here, these electrons, I use the same electrons which are generated by thermionic emission for heating a charge. Okay. So filaments are well shielded from the line of sight of both source and substrates. This eliminates contamination. Okay. All right. So the cathode potential is biased negatively with respect to a nearby grounded anode, anywhere from 4 to 20 kilovolts, because you need this accelerated, this potential for electrons to accelerate. And you can also use transverse magnetic fields to deflect the beam by about 270-degree arc, right? So it's a very simple process, you know. So you look at this diagram. So I'm producing the electrons there, okay, by thermionic emission, and then I have a flux of electrons. Now this is your crucible, yeah. This is a crucible there, and that is this whole thing is a charge. The whole idea is to heat only a part of the charge. And what do you do now? Well, we can easily manipulate the path of the electrons, is it not? Right? I can use a magnetic field, and the Lorentz force that is created on the electron using a magnetic field can make these electrons, the flux of electrons, to bend by almost 270 degrees. And I can make these electrons to directly come as a point source and impinge on the source there. See, the whole of green is here, the crucible with your charge. Now, only a part of the charge can be melted. And melting happens because you're talking about a few watts per centimeter square of energy density dumped down to the system. That's sufficient to, that energy is absorbed by the material. This energy is sufficient to break the bonds. That means sufficient to vaporize the material. And then this vaporization process is happening in very instantaneously. Of course, today we have electron sources where the peak energy densities can be as high as 10⁵ watts per centimeter square. Oh, that's a lot of energy, right? And this also we can make it in like a pulsed energy. So I create, I generate electrons, and then I can make an electron pulse to impinge on the source, bang, and with such a high energy, and that causes instantaneous melting because so much of energy is absorbed, causing evaporation. And again, as I told you in the beginning, we are also satisfying one condition that I'm using a point source. I mean, these sources can be just a few millimeters in diameter, if you're considering ideally circular sources. It's a beautiful way of dealing with the contamination problem, increasing the energy of the evaporated species. The evaporated species can have energies close to 30 electron volts here, all the way from change from 5 to 30 electron volts, which means when they go with those kinetic energies towards the substrate, which is also heated, the adatom mobility is much higher. So, so for all practical purposes where you need alloy coatings and coatings of elements for contacts or multi-layer growth, electron beam evaporation is a very popular process. It's a simple extension of thermal evaporation. It is still thermal evaporation. You are causing thermal evaporation by using electron beam of high energy. Okay, and this is how a typical electron beam multi-hearth source looks like. Today's multi-hearth sources can be 4, 6, or 8. That means I can have 8 such circles. Each circle is something like this one. What you'll have is, exactly like what you see here. Yeah, so like that. No? So I keep one charge there, another element there, another one. You can have 8 such different elements, which means if I want to do a multi-layer deposition, say one after the other, it's easy here. So this is the shutter, and so I can only expose one charge here. The electron beam evaporates. Then I can move the next one, third one, and by controlling the time and the amount of energy that is given to the system, I'll be able to get nice multi-layer deposition. Okay. Okay, there are there are issues here also. There are issues in every process. The thermal power and heating effects. Because see, I have a huge charge now. I'm dumping so much of energy to melt a small part of it, right? Now this energy that is dumped onto this large volume of the source, this whole energy can be absorbed, or there may be very less absorption, and this depends on many factors. The thermal diffusion length, to what extent the melting has happened, so that determines the thermal diffusion length. It also depends on the thermal conductivity of the material. It's very important. So there are 4 parameters that play a crucial role in causing the melting happen in a proper way. So one needs to estimate the total power that needs to be delivered by electron beam to the charge to compensate for heat losses incurred during the evaporation of, say, 10 raised to 18 atoms per centimeter square second. Right? It's not that you use the same set of parameters for all elements and alloys. Everywhere there needs to be optimization. The first point is the power density in watts per centimeter square that must be supplied to account for the heat of sublimation, delta Hs, the electron volts. And this works out to be something like 10 raised to 18 times 1 into 1.6 into 10 raised to minus 19 times the heat of sublimation. Again, these are all empirical relations, but these give good estimates. This works out to be something like 0.16 times. So you can estimate the power density that must be supplied to account for the heat of sublimation, and this heat of sublimation value has to be plugged in for each element that is present. The second one is the kinetic energy of evaporant. Of course, we know that it's 3/2 kbts per atom. So that the required power density pk is like that. So, so that is basically, that turns out to be 2.07 into 10 raised to -5 TS, where TS is the source temperature. This also has to be taken into account. The third one is, well, all these points are important, much more important, the radiation heat loss. There could be severe radiation heat losses. And if there's radiation heat loss, suppose the material radiates away all the heat, no melting happens, okay? And that is, of course, the famous, the T to the power of 4 law is applied here. And the radiation heat loss parameter is PR is equal to 5.67 into 10 raised to -12, epsilon times Ts to the power of 4 minus T0 to the power of 4. Where epsilon is a source emissivity, which is a very important parameter at the source temperature, and T0 is a room temperature. So using this relation, you can estimate the radiation heat loss there. And finally, the power density dissipated due to heat conduction through a charge of thickness L into the hearth of the whole thing. Because you're taking a large amount of the charge, and then the heat of conduction is very important to be estimated, and that goes as K times Ts minus T0 by L, and K is the thermal conductivity of the material. Thermal conductivity plays a very important role of the charge, right? So typically when you make all these estimates, the power densities required for metals work out to be 10 to the, something like 10 kilowatts per centimeter square, whereas for dielectrics, it is 1 to 2 kilowatts per centimeter square. You see that? Yeah? You try to understand why it is more for metals and less for dielectrics, even though the metallic bonds are weaker compared to dielectrics. Dielectrics are made of, inorganic systems, or it could be a combination of both inorganic and organic bonding, right? So that's what it is. So thermal evaporation, the first process that was invented long back, and a beautiful improvisation of that in order to avoid the crucible contamination is the electron beam evaporation, where, of course, you have to take care of all these parameters to successfully deposit a layer of single element or an alloy or multi-layers. Okay, good. So I'll stop there, and we will continue the lecture tomorrow morning at 10 a.m.